Leaderless replication. The replication approaches we have discussed so far in this chapter, single leader and multi-leader replication, are based on the idea that a client sends a write request to one node, the leader, and the database system takes care of copying that write to the other replicas. A leader determines the order in which writes should be processed, and followers apply the leader's writes in the same order. Some data storage systems take a different approach, abandoning the concept of a leader and allowing any replica to directly accept writes from clients. Some of the earliest replicated data systems were leaderless, but the idea was mostly forgotten during the era of dominance of relational databases. It once again became a fashionable architecture for databases after Amazon used it for its in-house Dynamo system. Roman 6 Riak, Cassandra, and Voldemort are open-source data stores with leaderless replication models inspired by Dynamo, so this kind of database is also known as Dynamo style. In some leaderless implementations, the client directly sends its writes to several replicas, while in others, a coordinator node does this on behalf of the client. However, unlike a leader database, that coordinator does not enforce a particular ordering of writes. As we shall see, this difference in design has profound consequences for the way the database is used. Writing to the database when a node is down. Imagine you have a database with 3 replicas, and one of the replicas is currently unavailable. Perhaps it is being rebooted to install a system update. In a leader-based configuration, if you want to continue processing writes, you may need to perform a failover. See handling node outages on page 156. On the other hand, in a leaderless configuration, failover does not exist. Figure 5-10 shows what happens. The client user 1234 sends the write to all 3 replicas in parallel, and the 2 available replicas accept the write, but the unavailable replica misses it. Let's say that it's sufficient for 2 out of 3 replicas to acknowledge the write. After user 1234 has received 2 OK responses, we consider the write to be successful. The client simply ignores the fact that one of the replicas missed the write. Figure 5-10. A quorum write, quorum read, and read repair after a node outage. Now imagine that the unavailable node comes back online, and clients start reading from it. Any writes that happened while the node was down are missing from that node. Thus, if you read from that node, you may get stale, outdated values as responses. To solve that problem, when a client reads from the database, it doesn't just send its request to one replica. Read requests are also sent to several nodes in parallel. The client may get different responses from different nodes, i.e. the up-to-date value from one node and a stale value from another. Version numbers are used to determine which value is new or see detecting concurrent writes on page 184. The replication scheme should ensure that eventually all the data is copied to every replica. After an unavailable node comes back online, how does it catch up on the writes that it missed? Roman 7. Sometimes this kind of quorum is called a strict quorum, to contrast with sloppy quorums discussed in Sloppy Quorums and Hinted Handoff on page 183. 2 mechanisms are often used in Dynamo-style data stores. Read repair. When a client makes a read from several nodes in parallel, it can detect any stale responses. For example, in Figure 5-10, user 2345 gets a version 6 value from replica 3 and a version 7 value from replicas 1 and 2. The client sees that replica 3 has a stale value and writes the newer value back to that replica. This approach works well for values that are frequently read. Anti-entropy process. In addition, some data stores have a background process that constantly looks for differences in the data between replicas and copies any missing data from one replica to another. Unlike the replication log in leader-based replication, this anti-entropy process does not copy writes in any particular order, and there may be the significant delay before data is copied. Not all systems implement both of these. For example, Voldemort currently does not have an anti-entropy process. Note that without an anti-entropy process, values that are rarely read may be missing from some replicas and thus have reduced durability, because read repair is only performed when a value is read by the application. In the example of Figure 5-10, we considered the write to be successful even though it was only processed on 2 out of 3 replicas. What if only 1 out of 3 replicas accepted the write? How far can we push this? If we know that every successful write is guaranteed to be present on at least 2 out of 3 replicas, that means at most 1 replica can be stale. Thus, if we read from at least 2 replicas, we can be sure that at least one of the 2 is up to date. If the third replica is down or slow to respond, reads can nevertheless continue returning an up-to-date value. More generally, if there are n replicas, Every write must be confirmed by W nodes to be considered successful, and we must query at least R nodes for each read. In our example, N equals 3, W equals 2, R equals 2. As long as W plus Rn, we expect to get an up-to-date value when reading, because at least one of the R nodes we're reading from must be up to date. Reads and writes that obey these R and W values are called quorum reads and writes. Roman 7 You can think of R and W as the minimum number of votes required for the read or write to be valid. In Dynamo-style databases, the parameters N, W, and R are typically configurable. A common choice is to make N an odd number, typically 3 or 5, and to set W equals R equals N plus 1/2 rounded up. However, you can vary the numbers as you see fit. For example, a workload with few writes and many reads may benefit from setting W equals N and R equals 1. This makes reads faster, but has the disadvantage that just one failed node causes all database writes to fail. There may be more than N nodes in the cluster, but any given value is stored only on N nodes. This allows the dataset to be partitioned, supporting datasets that are larger than you can fit on one node. We will return to partitioning in Chapter 6. The quorum condition, W plus Rn, allows the system to tolerate unavailable nodes as follows. Figure 5-11. If W plus Rn, at least one of the R replicas you read from must have seen the most recent successful write. If Wn, we can still process writes if a node is unavailable. If Rn, we can still process reads if a node is unavailable. With N equals 3, W equals 2, R equals 2 we can tolerate one unavailable node. With N equals 5, W equals 3, R equals 3 we can tolerate 2 unavailable nodes. This case is illustrated in Figure 5-11. Normally, reads and writes are always sent to all N replicas in parallel. The parameters W and R determine how many nodes we wait for, i.e. how many of the N nodes need to report success before we consider the read or write to be successful. If fewer than the required W or R nodes are available, writes or reads return an error. A node could be unavailable for many reasons, because the node is down, crashed, power down, due to an error executing the operation can't write, because the disk is full, due to a network interruption between the client and the node, or for any number of other reasons. We only care whether the node returned a successful response and don't need to distinguish between different kinds of fault. Limitations of quorum consistency. If you have N replicas, and you choose W and R such that W plus Rn, you can generally expect every read to return the most recent value written for a key. This is the case because the set of nodes to which you've written and the set of nodes from which you've read must overlap. That is, among the nodes you read there must be at least one node with the latest value illustrated in Figure 5-11. Often, R and W are chosen to be a majority more than N/2 of nodes, because that ensures W plus Rn while still tolerating up to N/2 node failures. But quorums are not necessarily majorities. It only matters that the sets of nodes used by the read and write operations overlap in at least one node. Other quorum assignments are possible, which allows some flexibility in the design of distributed algorithms. You may also set W and R to smaller numbers, so that W plus R less or equal to N, i.e. the quorum condition is not satisfied. In this case, reads and writes will still be sent to N nodes, but a smaller number of successful responses is required for the operation to succeed. With a smaller W and R you are more likely to read stale values, because it's more likely that your read didn't include the node with the latest value. On the upside, this configuration allows lower latency and higher availability. If there is a network interruption and many replicas become unreachable, there's a higher chance that you can continue processing reads and writes. Only after the number of reachable replicas falls below W or R does the database become unavailable for writing or reading, respectively. However, even with W plus Rn, there are likely to be edge cases where stale values are returned. These depend on the implementation, but possible scenarios include: if a sloppy quorum is used, see sloppy quorums and hinted handoff on page 183. The W writes may end up on different nodes than the R reads, so there is no longer a guaranteed overlap between the R nodes and the W nodes. If two writes occur concurrently, it is not clear which one happened first. In this case, the only safe solution is to merge the concurrent writes. See handling write conflicts on page 171. If a winner is picked based on a timestamp, last write wins. Writes can be lost due to clock skew. We will return to this topic in detecting concurrent writes on page 184. If a write happens concurrently with a read, the write may be reflected on only some of the replicas. In this case, It's undetermined whether the read returns the old or the new value. If a write succeeded on some replicas, but failed on others, for example because the disks on some nodes are full, and overall succeeded on fewer than W replicas, it is not rolled back on the replicas where it succeeded. This means that if a write was reported as failed, subsequent reads may or may not return the value from that write. If a node carrying a new value fails, and its data is restored from a replica carrying an old value, the number of replicas storing the new value may fall below W, breaking the quorum condition. Even if everything is working correctly, there are edge cases in which you can get unlucky with the timing, as we shall see in linearizability and quorums on page 334. Thus, although quorums appear to guarantee that a read returns the latest written value, in practice it is not so simple. Dynamo-style databases are generally optimized for use cases that can tolerate eventual consistency. The parameters W and R allow you to adjust the probability of stale values being read, but it's wise to not take them as absolute guarantees. In particular, you usually do not get the guarantees discussed in problems with replication lag on page 161 reading your writes, monotonic reads, or consistent prefix reads, so the previously mentioned anomalies can occur in applications. Stronger guarantees generally require transactions or consensus. We will return to these topics in Chapter 7 and Chapter 9. From an operational perspective, it's important to monitor whether your databases are returning up-to-date results. Even if your application can tolerate stale reads, you need to be aware of the health of your replication. If it falls behind significantly, it should alert you so that you can investigate the cause, for example, a problem in the network or an overloaded node. For leader-based replication, the database typically exposes metrics for the replication lag, which you can feed into a monitoring system. This is possible because writes are applied to the leader and to followers in the same order, and each node has a position in the replication log, the number of writes it has applied locally. By subtracting a follower's current position from the leader's current position, you can measure the amount of replication lag. However, in systems with leaderless replication, there is no fixed order in which writes are applied, which makes monitoring more difficult. Moreover, if the database only uses read repair no anti-entropy, there is no limit to how old a value might be. If a value is only infrequently read, the value returned by a stale replica may be ancient. There has been some research on measuring replica staleness in databases with leaderless replication and predicting the expected percentage of stale reads depending on the parameters N, W, and R. This is unfortunately not yet common practice, but it would be good to include staleness measurements in the standard set of metrics for databases. Eventual consistency is a deliberately vague guarantee, but for operability it's important to be able to quantify eventual